Okay, topic 11.3, capacitance. We have C, which is the symbol for capacitance. It has units of farad. So farad is the unit for capacitance. That's capital F. Equals charge stored in the capacitor divided by the voltage across the capacitor. When you add up capacitors in parallel, you do it directly. Capacitors in series, you have to add up the reciprocals of those capacitance values, and then you take the inverse to get the total capacitance. Capacitance equals the permittivity, either of free space or maybe a dielectric material in between the capacitor plates times the surface area of the plates divided by the distance separating them. The energy stored in a capacitor is 1/2 times the capacitance times the voltage across the plate squared. Tau is the time constant for an RC circuit. An RC circuit has a capacitor and a resistor. There's no cell in this for this level, so we just focus on a circuit that just has a capacitor and a resistor. So over time, the capacitor, which has stored charge, can dissipate its charge through the resistor. It happens much more quickly than a battery would lose voltage or charge. So a battery is not the same as a capacitor. So this time constant is the product of the resistance value in ohms times the capacitance C, or in farads. So this is the equation for discharging an RC circuit. The charge that's left inside the capacitor equals the initial charge times E, that's the natural log E, to the negative T over tau, and tau is R times C. Likewise, you can have how much current is left in your RC circuit. That's equals I naught E to the negative T over tau. Same thing with the voltage across, V equals V naught, which is the maximum voltage, times E to the negative T over tau. A capacitor is an electronic device that stores charge. It looks like this. In its simplest form, it's made up of two separated parallel plates, just like what we did in lab. In between the plates, we can have air, we can have a vacuum, or we can have a non-conductive material called a dielectric. So although there are other types of capacitors, in this study we focus on parallel plate capacitors. A schematic of a capacitor is shown. It's comprised of two parallel lines. Hey, that looks a lot like two parallel plates. An electrolytic capacitor has a higher capacity than the parallel plate capacitor. So that's another type. Electrolytes are in solution, but we don't focus on that for this level of physics. So capacitance, C, capital C, is defined to be the charge per unit voltage which the capacitor is capable of maintaining. The definition is given, C equals Q over V. The units for capacitance are coulombs per volt, which has a special name. It's called the farad, after Faraday, and it's abbreviated capital F. So capacitors, the more farads, the more charge per voltage you get from that capacitor. Don't confuse capacitance in farads with coulombs. So capacitance is a quantity. Coulomb is a unit. So just like resistors, capacitors can be wired in parallel. When in parallel, each capacitor obtains the cell's voltage. That should make sense because current will split, the voltage is shared evenly among the branches. So all I've done now is I've rewritten this equation for capacitance to solve for Q, multiplying by voltage on both sides. Q equals C times V, therefore the charge through branch 1 is C1 times V1, and the charge through branch 2 is C2 times V2. And from conservation of charge, I know that the charge coming out of the battery equals the charge through branch 1 plus the charge through branch 2. Current is split there. So the capacitance times the voltage is charge. the capacitance of the battery times the voltage supplied by the battery equals C1 times V1 plus C2 times V2. Since all of these voltages are the same, V1, V2, they're matching the EMF supplied by the battery, that means I can cancel all of these values. And that tells me that the total capacitance for parallel wiring is C1 plus C2. Okay, capacitors can be connected in series, as shown. Because the capacitors are in series, they each have the same charge Q. So in this case, Q from the charge from the cell equals Q1 plus Q2. Current can't go anywhere but through the line, so everything will get the same current. And since using the capacitor equation, C equals Q over V, we'll solve this for voltage. Voltage equals Q divided by C. Thus, Q over C is the same, or the voltage is Q over C. That means the voltage across capacitor 1 is the current divided by C1, and the voltage across capacitor 2 is Q2 divided by C2. Conservation of energy in this case tells me that the voltage supplied by the battery is equal to the voltage dropped by C1 and C2. So using the equation for capacitance, Q over V equals C, and I've solved it for V. The sum of the voltages is the same thing as Q over C of the battery equals Q1 over C1 plus Q2 over C2. And since, oops, the line wasn't very good. Since Q is the same for all three devices, all three objects, I can cancel out the Q, and I have 1 over C equals 1 over C1 plus 1 over C2. So this is for series capacitance. Note that the series parallel formulas for capacitance and resistance are reversed. Practice number 1. 3 capacitors, each with a capacitance of C, are connected such that their total capacitance, the combined capacitance, is 1.5 times C. How are they connected? So if they were connected in parallel for choice B, I would sum these, so this would give me 3 times the C, so I know it's not B. If they were connected in series, it would be 1 over C plus 1 over C plus 1 over C, which is 3 over C. You invert that, this becomes C over 3, so I know it's not A. So now I'm left with figuring out a combination that gives me 3 over 2C. So if I have 2 capacitors in parallel, this gives me 2C. Then I can treat these 2 parallel capacitors like they are in series with a single capacitor. So when I do that, I have 1 over 2C plus 1 over C, or this is 2 over 2C. This gives me 3 over 2C, and if I invert that, I get 2C over 3. Okay, so it's not D. Let's try this one. I have 2 capacitors in series, and they are in parallel with 1. So let's figure out the capacitance here. It is 1 over C plus 1 over C. That becomes C over 2, plus this extra branch, which is in parallel. So C over 2 plus 2 over 2C gives me 3/2 C. Choice C is the correct value. A simple capacitor consists of 2 conductors separated by non-conductive space. Thus, even the wires in an electronic circuit have capacitance. In extremely high frequency circuits, this inner wire capacitance can cause problems and must be minimized through proper design of these circuit boards. Capacitors are used in most electronic devices, and large capacity within a small space is a very expensive aspect of designing circuits. Capacitors are used as filters, coupling devices, voltage smoothing devices like with our full wave rectification, and in timing. When we want to have capacitance, again, having a high capacitance value within a small space is very important. So to increase the storage capacity, we use conductive plates instead of wires. So we have two ways to increase this capacitance. We can increase the area over which the charge is stored. Thus, the chargers can spread out and chill in their own personal space. Or we can decrease the distance between the plates and this makes it easier for the charges on one plate to be attracted to the other. Because the attractive force between charges is governed by the Coulomb's law, we see that the attractive force grows exponentially with this decreasing plate separation. Charge leakage can occur through air or vacuum. This means that you can have charges passing from one plate to the other. Manufacturers don't want this, so they'll place a non-conductive material called a dielectric between the plates. This reduces arcing, so it reduces a jump of electrons between the space and increases the storage capacity. So for a parallel plate capacitor, we have C equals epsilon, that's the permittivity of the dielectric material, times the surface area of the parallel plate divided by the separation distance between the plates. And please recall that epsilon is the permittivity of the dielectric, epsilon naught is the permittivity of free space and air. They're pretty close. The dielectric acts to reduce the electric field by a ratio epsilon naught over epsilon. It does this because the molecules in the dielectric get polarized in response to the electric field and create an oppositely oriented electric field. This helps to diminish some of the E field strength between the two plates. And from the equation Q equals C times V, and recalling that voltage is the electric field strength times the distance, I can see that Q over C equals voltage equals E times D, so that becomes capacitance equals Q divided by E times D. This means that the smaller the electric field is, the larger the capacitance, since you're dividing by that. Practice 2. A capacitor consists of two parallel square plates separated by a vacuum. The plates are 2.5 by 2.5 centimeters squares. The capacitance of the capacitor is 4.3 picofarad. Calculate the distance between the plates. So there are two equations we can use here. We can either use C equals Q over V, or we have another equation. We can use C equals epsilon times the area divided by D. Which do you think we should use? And if you said this one, you are correct. We should use the one on the left. What is the epsilon? Epsilon in this case is the permittivity of free space because it's separated by a vacuum. So our epsilon is epsilon naught, and that value is in the front of the data booklet. We need to convert these two from centimeters to meters. 2.5 e negative 2 times 2.5 e negative 2. The capacitance is 4.3 picofarad. What is pico? And you should be able to calculate the distance. The capacitor is connected to a 16-volt cell as shown. Calculate the magnitude and the sign of the charge on plate A when the capacitor is fully charged. So we need to figure out what Q is when it's fully charged and we want the sign. So this requires you to remember that the longer end of the battery is positive and the short end is negative. So this will help with the signs. And this is negative. Okay, we want the magnitude and the sign. So we are now looking for Q. So in this case, we can use C equals Q over V, and then you will solve for Q. The capacitor is fully charged, and the space between the plates is then filled with a dielectric of permittivity 3 times the permittivity of free space. Explain whether the magnitude of the charge on plate A increases, decreases, or stays constant. So we're going to have to analyze these two equations. Q over V equals epsilon times A divided by D. Okay, and I just multiply by V on both sides, so this cancels, so we can figure out what happens to the charge Q. Epsilon naught, this epsilon has tripled. Area stays the same. The distance stays the same. The voltage stays the same. So all that changes is epsilon naught. So please explain, does it increase, decrease, stay constant, and why? So from the relationship C equals Q over V, we can write that voltage is 1 over C times Q. Then we can make a graph of voltage versus Q, voltage versus charge, and it would have a straight line with a slope of 1 over C. Please remember that the work done by a cell is given by Q times V, and provided V and Q are constant, just provided that V and Q are constant. If they are not constant, work equals area under the V versus Q graph. Since the area of a triangle is 1/2 base times height, we have work is equal to 1/2 Q times V. From conservation of energy, this is then the energy stored in a capacitor. Energy in a capacitor is 1/2 Q times V, which is the same thing as 1/2 C times V squared. A parallel plate capacitor is connected to a cell of negligible internal resistance. The energy stored in the capacitor is 4 joules, and the electric field in between the plates is 100 newtons per coulomb. The distance between the plates of the capacitor is doubled. What are the energy stored and the electric field strength? So we will use the equation E equals 1/2 C times V squared to figure out how the energy changes, and then I will use this equation, capacitance equals Q over E times D. And this E is the electric field. I can rewrite this equation as E equals Q over C times D. And just so you know, this equation, E times D, is voltage. This comes from topic 10. And instead of D, they use delta R. And instead of V, it's delta V. So it's pretty much the same thing, the electric field strength. So I can see that when the distance is doubled, I can see how the electric field strength changes. Now likewise, I can use this equation up here, E equals 1/2 C times V squared, to figure out how the capacitance changes, because it's related to this. So the distance is still double, the D is on the bottom. If I plug into here, I should see very clearly both the energy and the electric field strength change in the same way. So let's say we have a capacitor that's been fully charged. It was fully charged because initially this capacitor was connected to position A, it charged up, and now we will switch this capacitor to position B. When we do that, we discharge the capacitor through the resistor. So the positive on the top plate travels clockwise through the wire and the resistor back to the bottom plate. If we use Kirchhoff's or Kirchhoff's, however you've heard it pronounced, rule for voltage, we see that following the loop in the direction of the current, we have the sum of the voltages in this loop equals 0. and that includes the voltage dropped across the resistor, so the voltage supplied by the capacitor minus the voltage dropped across the resistor equals 0. V is I times R. We will have the review of Kirchhoff's laws before the topic 10 and topic 11 exam. But since the voltage across the capacitor is Q over the capacitance, and since I equals a change in current over change in time, we have this expression now, Q over C, which is the voltage of the capacitor, minus R times a change in current over change in time equals 0. So I will add this, I have added R times Q over T to both sides, and I have divided by R on both sides to get change in Q over change in time equals negative Q divided by RC. The negative sign on the right-hand side shows that the change in Q is always negative during discharge. We're losing charge over time. The capacitor has its maximum value at the start, and this is diminishing. This is an interesting equation because I have the change of some quantity on one side equal to a product of that quantity on the other. Interesting. So we can rewrite these results of the RC, the resistor capacitor discharge, like this. I is change in current over change in time equals negative Q over tau, where tau is R times C. And then by doing a little bit of differentiating on both sides of the equation, we can get Q times Q naught. Q equals Q naught times e to the negative t over tau. As an aside, it's beyond the scope of this course, the exponential form comes from the associated differential equation dq over dt equals negative q over tau. It turns out that q equals q naught times e to the negative t over tau is its time-dependent solution. Many of the formulas we use in IB physics are easily derived using both differential and integral calculus. Although IB requires you to use the resulting formulaic solutions to the differential equations, you don't have to derive them. Trust me, you'll have plenty of time to learn about deriving linear differential equations in college. Okay, because of the relationships V equals Q over C and I equals V over R, we can also derive these next two equations. Q equals Q naught E times negative T over tau, where tau again is the RC constant. Keep in mind that V equals V naught E times negative tau times negative T over tau to the negative T over tau is the voltage across the capacitor and not the resistor. The resistor will have a starting voltage of 0. Kirchhoff's rule for voltage would produce the resistor voltage formula VR equals V naught times 1 minus E to the negative T over tau. So these equations given in your data booklet are only for the capacitor. And the IBO does not require you to know the charging formula. You only need to make sketch graphs for charging. So this equation coming up is not provided in your data booklet, but you might want to record it. Suppose we want to find the half-life of a charged capacitor. When is the voltage, the charge in the capacitor, or the current going to decay to half of its original value? So we can do V equals 1/2 V naught, and we will substitute into V equals V naught E to the negative T over tau. So I've replaced V with 1/2 V naught. Wow, that got skewed. V naughts cancel on both sides. I'm left with 1/2 equals E to the negative time divided by tau. I can take the natural log on both sides. ln of 1/2 equals negative T divided by tau, because the ln cancels the E. I have moved the negative sign to the other side of the equation, and negative ln of 1/2 is the same as ln of 2. So natural log of 2 equals T, where T is the half-life. That subscript is just denoting this is half the time, or the time it takes to discharge half of the energy, divided by tau, where tau again is RC. So this is the equation for half-life. the half-life equals tau ln 2. A capacitor of capacitance C discharges through a resistor of resistance R. The graph shows the variation with time t of the voltage V across the capacitor. The capacitor is changed to one of value 2C and the resistor is changed to one of value 2R. Which graph shows the variation with t of V when the new combination is discharged? So we'll use our half-life equation. T 1/2 equals tau times ln of 2. Just to see what we should be getting. Okay, so the voltage, I can tell from my answer choices, is staying at 1 volt. Obviously, we haven't changed the cell that the capacitor was connected to. But what's changed is tau. Tau is R times C. So originally, we have this tau ln of 2, and I can see that the half-life is around 0.4, it's kind of hard to see on my screen, but it's around 0.4 seconds. By having 2 times the current and 2 times the resistance, I have effectively increased the half-life by 4, by a factor of 4. So the new one, I don't know, I'm trying to distinguish this. Okay, I'll use a different color. So T 1/2 prime, I'm going to say that's the new half-life, equals 4 times the original half-life. So that means the voltage is at 0.5 around 1.6 seconds, because 0.4 times 4 is 1.6. So I need to look at the graph, and I need my choices, and I need to figure out about which graph best represents this. You want to see the voltage is 0.5 around when the time is about 1.6 seconds. Question number 5. A fully charged capacitor is connected to a resistor. When the switch is closed, the capacitor will discharge through the resistor. Which graphs correctly show how the charge on the capacitor and the current in the circuit vary with time during the discharging of the capacitor? So I know from discharging, that means that the charge over time will diminish. So already I can eliminate the last 2 choices. Another thing I know is that there's no way that the current is going to increase over time. All of this current is coming from the capacitor, which is discharging. Based on that, you can choose the right answer. Okay, so before I continue with this question, I just want to note I don't have any practice problems for you on charging a capacitor, but charging a capacitor is just the inverse of discharging. So if I were charging a capacitor over time, the voltage would increase. And if this was a discharge, it would be like inversely proportional. It would be the inverse. Not inversely proportional, but the graph would look like the inverse. Okay, let's start with number 6. A negatively charged thundercloud above the Earth's surface may be modeled by a parallel plate capacitor. The lower part of the capacitor is the Earth's surface, and the upper part is the base of the thundercloud. The following data are available. Area of thundercloud base is 1.2 times 10 to the 8 meters squared. Charge on thundercloud base, negative 25 coulombs. Distance of thundercloud base from Earth's surface is 1,600 meters. Permittivity of air, 8.8, E negative 12 farad per meter. Show that the capacitance of this arrangement is 6.6 times 10 to the negative 7 farads. So for this, we will use this equation. C equals epsilon times the area of the plate divided by the distance. All of that is provided. Plug and chug. Part B, calculate in volts the potential difference between the thundercloud and the Earth's surface. So once you have calculated the capacitance, C equals Q over V, and then you have C, you can solve for V. Calculate in joules the energy stored in the system. This is easy. The energy stored is 1/2 C times V squared. You have V from the last problem, you have C from part A, you can solve it. Lightning takes place when the capacitor discharges through the air between the thundercloud and the Earth's surface. The time constant of the system is 32 milliseconds. A lightning strike lasts for 18 milliseconds. Show that about negative 11 coulombs of charge is delivered to the Earth's surface. Okay, so we're discharging the circuit, we're discharging the capacitor, so we're going to use this equation. Q equals the initial charge Q naught times E to the negative time over tau. Now, when I calculate this Q tells me how much charge is left over in the system, or how much charge is still stored. Q naught is the original amount of charge, which from the previous slide or on your paper is negative 25 coulomb. We are given the time, so we're going to say from 0 at a time of 18 milliseconds, that's when lightning strikes. Tau is the time constant, and that's 32. So the charge that's still stored equals negative 25 times e to the negative 18 divided by 32, the millis cancel. You'll get a value. Now this value you get is not the charge delivered to the Earth's surface. This is the charge that is still stored inside of the capacitor. To get the charge delivered to the Earth's surface, you'll have to subtract this value Q from the original, and this will give you how much charge was transferred via lightning to the Earth's surface. Calculate in amperes the average current during the discharge. So in your minds, you might be thinking, okay, is this the current in the capacitor? Is this the current with the lightning? Well, it's both, because the lightning is essentially a movement of charges. So we are looking at the current that is transferred via lightning, and we couldn't have that lightning without this capacitor. So the current is change delta Q over delta T, and I know that lightning lasts 18 milliseconds, and I know how much charge, the change in charge that was transferred from the thundercloud to the Earth's surface, and I know that was around 11 coulombs. So you can calculate, but I want you to use the value that you got in part D with 1 decimal place with 3 sig figs. So this needs to have 3 sig figs, and it can't be 11.0. And I want you to use this to calculate the average current during the discharge. Okay, so this requires a little bit of critical thinking. State one assumption that needs to be made so that the Earth thundercloud system may be modeled by a parallel plate capacitor. There are several assumptions. You can look at your equation first of all. Your equation C equals epsilon times A over D. We need to assume some things are constant about the situation. You can choose, maybe the distance should stay constant. Maybe we have to assume that the thundercloud and the surface of the Earth are totally parallel. There are several assumptions that can be made. This is a 1-mark question.